In this video, we'll review 1D tensors, review some common operations that you'll likely use when building a network, reprocessing your data, or analyzing your results. Tensors are essentially arrays, but before you build a neural network, you must learn the basics of tensor operations, data types, indexing and slicing, basic operations, and universal functions. Let's go over the basics. A 0D tensor is just a set of numbers. For example, we have 1, 2, 0.2, and 10. A 1D tensor is a simple array of numbers. For example, a row in a database, a vector, or a time series. Tensors contain elements of a particular data type. The tensor type is the actual type of tensor. We have real numbers such as floats and doubles. We have positive unassigned integers using 8-bit images. And we have signed integers. We can create a tensor from a list. First, we import PyTorch. Then we cast a list to a tensor. We can access each element in the tensor via index. Just like a list, the elements correspond to an integer with a square bracket. We can use the data attribute dtype to find the type of data stored within the tensor, in this case, int64. We can use a method type to find the type of tensor. In this case, we have a long tensor. In this example, we create a float tensor, as the elements in the list are floats. We can use the data attribute dtype to find the data stored within the tensor. In this case, the type is float32. We can use a method type to find the type of tensor. In this case, it's a float tensor. We can explicitly create a tensor of a specific type. In this example, we create a float tensor by using the function floatTensor. When we check the type of the tensor, we get a float tensor. We can see the tensor has decimals when printing it out. We can change the type of tensor. Consider the following long tensor. We can convert the tensor to a float tensor as follows. We can verify the type of tensor has changed. We can cast the following list to a tensor. The method size is the number of elements in the tensor. As there are 5 elements, the result is 5. The attribute ndim represents the number of tensor dimensions, or the rank of the tensor. In this case, it is 1. In many cases, PyTorch functions may require a 2-dimensional input. In this case, we have a 1-dimensional tensor with 5 elements. We can use the method view to add an extra dimension. The first element represents the number of rows, in this case 5, and the second element represents the number of columns, in this case 1. If you didn't know the size of the tensor was 5, you can replace the 5 with a -1. Let's see another example to clarify this. In this example, the tensor has 6 elements. As before, we can reshape the tensor, but as there is 6 elements, we use a 6 instead of a 5. Similarly, we can replace the 6 with a -1. It's not difficult to convert a PyTorch tensor to a NumPy array and convert it back. This gives PyTorch the ability to work within the Python ecosystem. Many Python libraries return or require NumPy arrays. Consider the following NumPy array. We can convert the NumPy array to torch tensor using the function from NumPy. We can convert the torch tensor back to a NumPy array using the method NumPy. Let's represent the NumPy array with this blue box and the torch tensor with this red box. Finally, we'll use this blue box to represent the variable back to NumPy. The variable back to NumPy points to the variable torch tensor. The variable torch tensor points to the variable NumPy array. Therefore, if you change the variable NumPy array, both torch tensor and back to NumPy will change. You will see an example of this in the lab. We can convert a panda series to a torch tensor in a similar manner. We simply use the attribute value to convert the series to a NumPy array. We then use a function from NumPy to convert it to a torch tensor. We can use the method toList to return a list from a torch tensor. Individual values are also tensors. Consider the tensor this tensor. In many cases, we would like to return a Python number. The first element of the tensor is given by the following, and it is also a tensor. Similarly, the second element is given by the following. We can use a method item to return a Python number for each element of the tensor. For example, we can return a Python number for the first element as follows, Similarly, we can do the same for the second element of the tensor as follows. Let's review some indexing slicing methods that you can use to access a particular value or set of values stored in a tensor. Consider the following tensor. We can change the first element of the tensor to 100 as follows. The tensor's first value is now 100. We can change the fifth element of the tensor as follows. The fifth element is now 0. We can slice a PyTorch tensor just like a Python list. The elements of the tensor correspond to the following indexes. We can select the elements from 1 to 3 and assign it to the new tensor D as follows. The elements in D correspond to the following indexes. We can assign the corresponding indexes to a new value as follows. The tensor C now has the new values. PyTorch makes it easy to do many operations that are commonly performed in neural networks. Let's review some of these operations on one-dimensional tensors. We'll look at many of these operations in the context of Euclidean vectors to make things more interesting. Vector addition is a widely used operation. Consider the vector u with two elements or components. The components are distinguished by different colors. Similarly, consider the vector v with two components. In vector addition, we create a new vector, in this case z. The first component of z is the addition of the first component of u and v, respectively. Similarly, the second component is the sum of the second component of u and the second component of v. The new vector z is now a linear combination of the vector u and v. We can also perform vector addition with one line of PyTorch code. Vector multiplication with a scalar is another commonly performed operation. Consider the vector y. As before, each component is specified with a different color. We simply multiply the vector with a scalar value, in this case 2. Each component of the vector is multiplied by 2. In this case, each component is doubled. In PyTorch, we can multiply a tensor by a scalar as follows. Hemorrhoid product is another widely used operation. Consider the following tensor or vector. The result of the hemorrhoid product of u and v is the new tensor z. The first element of z is comprised of the first element of u and v. Similarly, the second element is the product of the second element of u and v. The resultant is a new vector that consists of the element-wise product of u and v. In PyTorch, we can also perform hemorrhoid product with one line of code and assign it to the tensor z. The dot product is another widely used operation in neural networks. Consider the vector or tensor u and v. The dot product is a single number which represents how similar the two vectors are. We multiply the first component of u with the first component of v. We then multiply the second component of u with the second component of v and add the results together. The result is a number that represents how similar the two vectors are. Just a note, we'll drop the transpose operator in the course. We can also perform dot product on PyTorch using the function dot and assign it to the variable result as follows. Consider the tensor u. The tensor contains the following elements. If we add a scalar to the tensor, PyTorch will add the scalar to each element of the tensor. This property is known as broadcasting. Now let's discuss applying functions to tensors in PyTorch. Consider the tensor A. We can calculate the mean or average value of all the elements using the method mean. This corresponds to averaging all the elements in the tensor. In this case, the result is 0. There are many other functions. For example, consider the tensor B. We can find the maximum value using the method max. We can see the largest value is 5. Therefore, the method max returns a 5. We can use torch tensors to create functions that map tensors to a new tensor. Let's implement some code on the left side of the screen and see what's going on the right side of the screen using vectors. We can access the value of numpy as follows. We can create the following torch tensor in radians. This corresponds to the following vector. We can apply the function sine to the tensor x and assign it to the tensor y. This applies a sine function to each element in the tensor. This corresponds to applying the sine function in each component in the vector. The result is a new tensor y, where each value corresponds to the sine function being applied to each of the elements in tensor x. A useful function for plotting mathematical functions is line space. Line space returns evenly spaced numbers over a specified interval. We specify the starting point of the sequence and the ending point of the sequence. The parameter num indicates the number of samples to generate, in this case 5. The space between samples is 1. If we change the parameter num to 9, we get 9 evenly spaced numbers over the interval ranging from -2 to 2. The resultant difference between subsequent samples is 0.5, as opposed to 1, as before. We can use the function linespace to generate 100 evenly spaced samples from the interval 0 to 2 pi. We can then use the PyTorch function sign to map the tensor x to a new tensor y. We can import the library pyplot as PLT to help us plot the function. As we're using Jupyter notebooks, we can use the command matplotlib inline to display the plot. The following command plots the graph. The first input corresponds to the x value. We have to convert the tensor to a NumPy array using the method NumPy. The second input corresponds to the y value, or y-axis. Similarly, we have to convert the tensor to a NumPy array using the method NumPy.